And that was Fleetwood Mac and Sunny Side of Heaven. And if that means rain, then we've got it today. Forecast, I thought, didn't ask for it, just clouds. And walk outside and whoa, we have rain. We also have a lab due today. It's the next to the last lab. And just a reminder, the last lab will be due next week on Thursday as we finish up the week and the semester before finals. The material for today involves the chi-square, and so we're going to talk about that. We collected the homework from the 1 and 2 sample problems with hypothesis testing for proportions. We had a problem on the board yesterday that we could have done with chi-square. I didn't leave it up there because I needed the board for the subsequent class, but I'd like to go to the chapter on chi-square. And I'd like to go to 564, if you would please, in your text. And the point I made, before we go there, just a comment in general, I made the point that our density curve, when we have 1 degree of freedom, was really like the tail of the chi-squared density curve. I'm on 564. So let's go to the document camp. And you'll note the shape of the density curve based on degrees of freedom. And when you look in particular at what we see when you have 1 degree of freedom, it's just a portion of the tail of the curve. Okay, it is this portion up here. So it starts up here and comes down. So when you draw your density curve for a hypothesis test, if you have 1 degree of freedom, you're going to have an area to the right of my pen on that one part of the curve that looks like a tail of the curve, and that's all you draw. It's not until you get up to 4 degrees of freedom or 5 degrees of freedom that you start getting this more or less classic look to it, and then at 8 degrees of freedom it's starting to look a little bit more bell-shaped like, but still note, you don't have a tail of the curve on the left side. So density curves for chi-squared look somewhat different. We illustrated this past week page 565, and this was the chi-square test and the z-test. Now, I'm going to leave that on screen just for a bit more, and what I want to point out to you as I go to the board on this, that the null hypothesis, when we look at a z-test, is going to be P1 equals P2 for the 2 sample variety. And we have P1 not equal to P2 as a kind of default we can take. But keep in mind, this can be greater than, it can be less than, and why again might we want to do the one-tailed? What's your argument? More power. Agreed. You have more power in doing it this way. Now, if you're going to consider the chi-square, you cannot do either of these two. The chi-square as an alternate is simply not equal. So back to the document cam. When we make a comparison between the chi-square and the z-test, we get exactly the same p-value, as long as, coming back to the board, we're doing an alternate of P1 not equal to P2. Okay. The other thing to keep in mind, and just to sketch it roughly, this is your chi-squared density curve for 1 degree of freedom. And note, when we do this, even though in the chi-squared we have not equal up here, all of our 5% go here. As opposed to the z-test, where you split 2.5% in each tail for this alternate. Another note, you have to have degrees of freedom to reference the table to find a critical value. And just like the problem we have with the t-test, you have to have degrees of freedom in order to get the decision rule, but it's difficult to get the p-value unless you resort to stat graphics. Now, I used an HP calculator to get the area in the tail of the curve for a particular value of chi-squared. Again, with the table in the back of the book, all you can do is give an interval estimate. So the problems with the t and the chi-squared are very similar when it comes to using the table. And we've illustrated that. Now, I made a comment to you also, as we come back to the board, sorry about that, Jennifer, that this was a test of equal proportion. And that's going to be important because the language we use in chi-squared contrasts this to some other tests that you can do. So, for example, in this problem, I'm arguing that two populations are homogeneous relative to what I'm measuring. So if I'm talking about proportion of high births, then I'm saying the 6 continents are homogeneous relative to that. Now, we sometimes refer to this as a test of heterogeneity as opposed to homogeneity. I think it's probably easier just to think of it as a test of equal proportions. However, this test statistic, and let me just write it out again. Now, we write a Greek symbol. It's spelled C-H-I, but it's pronounced chi, like a kite. And we say it is a summation, and we have an O sub I, that's the observed value, minus the expected value. Is the author using big E's or little e's in this? Do you know? Little e's? Okay, so I'll use the little e. My objection to the little e, it reminds you of the errors we had in bivariate data analysis. But nonetheless, we can do that. You subtract the expected from the observed in each cell and square the difference. Then you divide by that expected value. That is our test statistic. And just a reminder, these e's can be found by taking the row total, multiplying by the column total, and dividing by the grand total. So we have a nice little formula that we can generate values of E for our contingency table, our 2x2 table in this case. But the advantage of the chi-square, as you found in the lab, is that you can go beyond 2 samples, 3 or more. Now, I mentioned one way of remembering at least the elements of this formula is the old McDonald's had a farm with the EI, EI, OI. But one of the advantages of chi-squared and ANOVA is that you can do 3 or more population parameters in your null hypothesis. So there's another little ditty we do in childhood, 1 potato, 2 potato, 3 potato, 4. 1 sample, 2 samples, 3 samples or more. Same idea. And the chi-squared and the ANOVA allow you to do 2, 3, and 4 and more. The Z or the T, whichever we're using, are restricted just to 2 samples. The advantage of the T or the Z is that you have a one-tailed alternate you can do, and hence more power. Okay, using this test statistic, we can do 2 other hypothesis tests that are talked about in this chapter. And we do the same calculation. One is a test of independence. And to contrast the test of equal proportion. The equal proportions assumes you have 2 or more populations. You're arguing that those populations have the same proportion of whatever it is you're measuring. So if we were measuring high birth rates, again, the argument, the proportion of high birth rates is the same across the populations. A test of independence looks at a single population and talks about some characteristics within that population and asks if they're independent of each other. Okay? Now, if we looked at a population of business students, and one of the problems in the homework deals with that, and we looked at the choice of majors based on 2 characteristics, the majors involved and gender. Would you argue that there's an independence between the choice of major in a business school and whether you were male or female. Okay. There was a time, for example, in engineering, when I was a student in engineering, that was my first major, civil engineering, for a couple of years, and so that meant you had a sort of a multi-major. You had a major in mathematics, a major in chemistry, a major in physics, a major in engineering simultaneously. And so what was most noticeable were nearly all the classes were filled with men. It was a rarity to see a young lady in a class. Now, you walk into a calculus class, and you might have more women in there than you do men. But there has been a time when business was more open to men than to women. And we talk about a glass ceiling, and you understand what I mean by a glass ceiling? Is that a familiar phrase to you? Some nods yes, some not. A glass ceiling suggests that if you are a young lady and you want to become a CEO, there's some kind of inherent limitation to getting to CEO status in companies. And it's interesting, in the last month or so, reading the Wall Street Journal and the New York Times, there are still references to glass ceilings out there, that it is much more difficult for a young lady to get into management compared to a man. And so the argument might be that in business schools, by major, you might find choices are being made based on what is perceived as an open or non-open field. So somebody wanting to go into accounting versus somebody who might want to go into marketing, it might be perceived that it's a little more open in one area than the other. Now in accounting, it seems that it's a very balanced field at this point. Marketing might even be more open to a woman than to a man. But if you're thinking in terms of the field of economics, that again tends to be dominated oftentimes by men, and part of that was the amount of mathematics that was necessary to get a degree in economics. So independence, we'd like to compare that. There's a classic problem in the text, although it's been relegated to not quite the central position it was, and it had to do with the Titanic in 1914 thereabouts. And the Titanic, as it went down, you're well aware that there was a large number of people who died, and that's been popularized in the movie with Leonardo DiCaprio and Kate Winslet, and the idea was that not enough lifeboats and so on. But the question, was the proportion of deaths independent of gender or status? And so in particular, what's interesting is if you just take men alone, then you look at the status. Was dying on the Titanic independent of your status? Now, in a ship, a luxury ship, such as the Titanic was, if you had money, where were you tending to have your accommodations? Topside. And if you had no money, you were down by the engine room. Okay? And if there is something like that catastrophic collision and you have to evacuate immediately, who has closer proximity to lifeboats? Those who are in top. And so it's sort of a no-brainer that status, money, related to having more access to an escape route than if you were down near the engine room and going up maybe 5, 6 flights of stairs. But that idea of something, two characteristics, the characteristic of death, not dying, and status, are they independent of each other? So that's what this is about. Let's take another one. A test of, let's see, let me give you the example first, and then I will talk about it in terms of a title. I don't know what kind of jobs you've had as a student. The jobs I had as a student going through, oftentimes in summers you were a recent hire, and so you didn't get the day shift. You got the night shift. And so oftentimes it meant rotating night shifts. That is, you had the swing shift at 4 to 8, I should say 4 to 12, 8 hours, and then you had a graveyard shift from midnight to 8 a.m., and you tended to get those shifts if you were a new employee in the summer and not going to be staying with the job. Are you familiar with how seriously industry looks at the accidents that occur in a plant? If you were to walk through any manufacturing area, you would usually find some sign that says there's been 1,000 days since any accidents, celebrating the idea no injuries, no lost time. And why is that so? Why are they concerned about accidents?
Because it slows production down, liability.
Okay, production down would be one answer. Liability is a bigger one. If somebody gets injured, you suspect there's going to be a lawsuit. And the Human Resources Department will oftentimes, in order to avoid a lawsuit, settle out of court. It's costly, it's time-consuming, and so the best thing to do is avoid the accidents. Okay? Now, with that in mind, I could go ahead and I could look at 3 shifts, and let's just say this is day, swing, and GY for graveyard. Now, with this in mind, let's say that you have a company, a construction company, building modulars in a plant, and you run 24/7. So that means you're running 3 shifts, 8-hour shifts. And let's say, for whatever reason, you have a number of accidents that have occurred in the past year. And in the day shift, you have 1. And in the swing shift, you had 3. And in the graveyard, you had 8. Now, this is extreme. But nonetheless, the idea being that you have an unequal number of accidents across the 3 shifts. What would you expect if there was no difference between the shifts in terms of accidents? An equal spread at 4, correct? Okay, so we could put like a diagonal here and say there should be 4 here, there should be 4 here, and there should be 4 here. Okay. Now, with this in mind, I can take the same test statistic that I had before, and this is an easy one to do. The degrees of freedom will be 2, 1 less than the number of categories. So our degrees of freedom, 2. And it doesn't work to do our usual formula. Our usual formula for degrees of freedom was what? R minus 1 times C minus 1. But I only have 1 row and 3 columns, so I get 0. So we just take the number of categories. That's 3. Subtract 1, and we get 2. So if I look at the differences here, 1 minus 4, and square that and divide by the 4, that's my first cell. My next cell is 3 minus 4. Square that and divide by 4. And my last one is 8 minus 4. And divide by 4. And what do we get when I add all this together? Well, here I'm going to have 16 over 4, correct? So that'll just be 4. Here I have minus 1 squared over 4, so that's 1/4. I'm sorry, I screwed that up. I was thinking I had 0 minus 4 there, so my error. I did not note the 1, thinking I had just 4. So instead, this would be 3 squared, which is 9 over 4, correct? My apologies there. And this one I have the 4. Square that, I do get 16 over 4. And since I have a common 4 up here, it might make sense just to do 16 over 4. So when I add these, I have the 9, the 10, the 16, 26 over 4. So if I add all this together, 26 over 4, or 13 over 2, or 6.5. Now, 2 degrees of freedom. So if I look at this, something like this for the degrees of freedom curve, and I have 5% here, I need a critical value. Will you now go to the text, and I need to find what page that table is on, so I'm going to come back center, Jennifer. Okay, let's see what we can do page-wise. I need to mark where we are. Is it 692? Thank you, Daniel. 692. And this is the generic-looking curve. Let's look at that for a moment. We're at 2 degrees of freedom, so coming off there for just a moment. And we have, as we look at this now, 2 degrees of freedom, and we want to come over to where we just have 5% in the tail of the curve. So that's at the end of the screen for what I've tried to illustrate there. And we have our 5%, our 2 degrees of freedom, so we have a 5.99, correct? 5.99. So what I'm going to do is come back here, put this in, 5.99, and my decision rule would be what? To reject. Now in this case, that we have equal number of accidents per shift. I want to say that in a little different way here momentarily. But we would reject the null hypothesis that I haven't stated it as such. If my chi-squared value is greater than or equal to the 5.99. And what was my value? 6.5. So my conclusion is to reject h sub 0. Now, this particular hypothesis test is referred to as goodness of fit. And the notion is, does your data fit a known distribution? Now, the distribution we are arguing here, if you'll allow me to reflect back to many of the different things we've done in these past weeks and months, a uniform distribution. We are saying there's a uniform distribution of accidents as we come back to here a little bit. Thank you, Jennifer. It's uniformly spread out here. We expect 4 in each one. So a discrete uniform. Now, the last time we really focused on a discrete uniform was when we did a random sample from 1 to 226 or thereabout, and we said each value had the same chance of being obtained. Well, this is uniform discrete in the sense that I expect a uniform distribution of the accidents per the 3 shifts. Does my data fit the expected? And the answer here is no. Now, we could use this same idea to check for normality. And that's one of the reasons I like to bring this up. Because in normality, we have certain expectations also. So if I look at a normal distribution with, say, 100 pieces of data, and I break it into 6 regions, plus or minus 1 standard deviation, plus or minus 2 standard deviations, plus or minus 3 standard deviations. So let me just sketch as we come over here a little bit further. And I draw the curve centered at mu. And then I go over where the curvature changes on each side. I'm hoping that they look about the same distance. And the argument is that I have 68% of my data in there, correct? So if I had 100 pieces of data, I would expect to see 34 here and 34 here. Now, I can go ahead and come over another standard deviation. And I know between there's 95%. Right? within 2 standard deviations. So that means 47.5 on each side. Okay, and I know there's 2.5 here, so I could argue that in this third region, I should have 2.5 pieces of data. Your expected values do not have to be integers per se. Let's bring that in maybe a little bit tighter. I'm seeing that a little bit difficult to read, Jennifer. Thank you. So what does that leave for here? If I've got 36.5, and I have 47.5, so what does that leave for here? I should say 50. My apologies. If I have 36.5 and I'm supposed to have 50 here total, what's left for here? 50 minus 36.5. In your head? 13.5? Thank you. So those are my expected values. And I could look at a data set with 100 pieces of data and ask, how many pieces of data do I have in each interval? It's a little bit like the normal probability plot when we talked about the ogive. Now, what would be your critique here for these expected values? You should be able to give me a critique. There is an assumption, a requirement. And what is that requirement about the EIs, the expected values? They must be how large?
30.
No, not 30. The 5 or more, right? I have these two at what? Under 5? What percent did I say you could have under 5? 20%. Okay, if I have 6 intervals and 2 of them are missing the requirement, I have 2 out of 6 is 33.33%, so what am I losing? Power. So what could I do? Combine. And so combine these two together, and I'm really at what? 4 columns now, and I would be okay. So if you were wanting to establish normality, you could say, in this last group, I expect 16. I expect 16 here. And then just see how many you have. First exam. A reasonable question in the first exam, and thinking of the final and reviewing the first exam, a reasonable question would have been, here's your data. Will you find the number of pieces of data in each of these intervals? And I ask you to do plus or minus 1, plus or minus 2, plus or minus 3 kind of thing. And then I said, discuss the results. Does this meet the empirical rule? So if you expect 68 here out of 100, or if you have a smaller data set, and you certainly had a smaller data set, you expect 68%. Well, if you get 50%, does that suggest you have normality? No. Same concept. Now, if you have a sample, this was n equals 100. If you have a sample of 100, do you worry about normality in your population? Why should you not worry about normality? It's a 3-letter abbreviation, the CLT. Because 30 or more, you're guaranteed your means are going to have an approximately normal distribution. So this isn't much of a concern. When does it become a concern? When I'm under 30. Down at 15. Between 15 and 30. Maybe at 10. So cross out a 0. Is it reasonable to do this if you're down at 10 instead of 100? Well, all I have to do is move the decimal over. Okay. Oh, that was bad. 1.6. So I have 3.4, 3.4, 1.6, 1.6. Those are my expected values, and are they all under 5? Yes. So when I need it most, it's not very effective. But it is, nonetheless, a way of comparing if you have data that fits a known distribution. So it's not a bad idea. This goodness of fit. So let's swing back here. Goodness of fit test. And just a comment here that if you are in the area of business, it's a nice, straightforward test to show that statistically speaking, there's a significant result. Now, I can guarantee you that you wouldn't need statistics to go to the CEO and say, we have a problem. 1 accident here, 3 accidents here, and 8 here. This is unacceptable, and you aren't going to need a statistical analysis to carry that point. But it would be nice if you had it available. By the way, what would account for this larger number here? Have any of you worked in swing or in the graveyard shift? Anybody in here at all? 1, 2 of you? What happens in graveyard? You're tired. Okay, very good. It's really difficult to get sleep during the day and when you think you should be out partying. And what else? You're tired and delirious. Well, maybe. Without enough sleep, you might be. What kind of things are available to you in a graveyard shift compared to a day shift? So, for example, you'd like a cup of coffee. You'd like to go to the vending machine. At 3 a.m. in the morning, the vending machine's empty. It will not be restocked until 8 a.m. The coffee machine quit working at about 11 o'clock at night. It jammed the cups, and it won't be serviced until 8 o'clock in the morning. In the current economy, they've probably shut down half the lights to save energy. So the lighting is bad, and nobody wants to work the night shift, so you don't have the best supervision, if any. Oh, and by the way, the nurse isn't available during the night shift at midnight to 8. Human resources not available midnight to 8. And you have a break, but you can't do anything on the break because there isn't anything to eat or drink. You're tired, not feeling well, and don't give a rip. Attitudes become a problem, and accidents go up. Now, I've painted a pretty gruesome picture, a pretty bleak picture, but I've also worked in jobs where that was pretty close to a reality, where it just was not the place to be. And then the way about, in a sense, was to rotate shifts. If either of you two rotated shifts from swing to graveyard, day, and so on, your biological clock really gets screwed up. About the time you've adjusted to going to sleep at 9 o'clock at night and getting up at 11 for 2 hours sleep, and then work 8, and then you go to graveyard from that to day shift, you get so messed up you don't know when you're sleeping. Very real problem. Let's come back to the test of independence. I'm going to come to the text, I'm going to come back center, because you're doing the same thing in each of these problems. Nothing is different other than the null hypothesis. That's the difference. So in a test of goodness of fit, we would argue that the distribution, your data fits a particular distribution. So this was a uniform distribution, so that you had equal accidents per shift in the one we just did. For a test of equal proportions, it's just P1 equals P2 equals P3. See, when you have the test of goodness of fit, you tend not to do it with symbols. You just tend to write it out in an English sentence. The test of independence will say 2 characteristics are independent of each other. So major and gender are independent in this population of business students. Okay, goodness of fit test is covered for you on 566. And I'm not getting quite, let's see if I can do anything here to brighten this up. Okay, let's try that. Goodness of fit. That's on page 566. And the discussion here is the number of babies born in this particular problem. It's a rather fascinating one. The number of babies born per day. And so in this case, the argument is the number or the proportion of babies born per day is the same. Equal distribution. And by the way, why would this, do you think, not work? Why do you think there might be a significant difference?
Well, just because doctors and nurses would want to work on Sundays?
That's not a bad statement. Sean's saying doctors would like the weekends off. Can you control when the baby's coming?
Medications and
Called a cesarean, C-section. And it's more convenient to do it Wednesday, so you're due Friday or Saturday, we'll do it Wednesday so you can have the day off on the weekend. Look at the numbers. 24 and 20 on a Tuesday and Wednesday, 23, 24, 20, 27 on a Thursday, and then Sundays and Saturdays? No. Not going to happen if you can avoid it. Okay? Now notice the null hypothesis in this case was simply that the proportion is 1/7. So that was one way of saying equal proportions for these 7 days of the week. For the goodness of fit I just did, we could have said that you have 1/3 of your accidents on each shift. Or you can just say there is an equal distribution of accidents per shift. Okay, so there's a problem you can go through. The statement on page 568, this is the little box for goodness of fit, just for what it's worth. Then coming off that, I need to back up because the uses of the chi-squared, I'm hunting for a statement that I always have trouble finding, and it's basically under the category other uses of the chi-squared distribution. And it's where he's talking about tests of independence. And he doesn't give a very good example, and I'm not going to spend too much time hunting for it. I know it's somewhere in the region of 560, where he talks about the uses. There it is. Okay, this is on page 560. And he comments two-way tables can arise in several ways. And we talk about, let's see, as we come down here, this is where all the data comes from just one sample. And this is a case in which, as we come off there for a moment, we are dealing with proportions. And let's see if I can find, there it is. On 562, finally. He's talking about the hypothesis of no relationship between two variables within a particular population. And so, in this case, on page 562, he identifies the idea of independence. And the box right at the bottom of that page, uses of the chi-squared, he states it in terms, no relationship between the two variables. I usually state it as the characteristics are independent of each other. That's saying the same thing. And so, in this case, you have, at the very bottom, an SRS, an individual classified according to two categorical variables. So that's where we get two categories. So according to two categorical variables. And so we say a single population, we can compare classifications by categories and determine if the categories are independent. And the example I was referencing, as we come off there, is on page 563. And this is where I was talking about accounting, economics, administration, and finance. And if you'll think of the glass ceiling, I was rather surprised with this data. Because look at the percent, or not the percent, but the number of females looking at administration. It's better than a 2-to-1 ratio here. And this is where the glass ceiling often prevails. So in this particular business school, which was the University of Illinois, that was a surprising result for me. And so the question, as we look at this data, would you argue that there's an independence of major relative to gender? So as we look at the data again, you have in essence your table. It's no longer 2 by 2, correct? It's 2 by 4. So what is your row total in each case? Will you write those in? If you don't like writing in your book, then do it somewhere else. But what is our row total for that first row for accounting? We have 56 and 18. That would be 100 and what? 124? Is this going to work? Not well. Okay, let me change what I'm doing here. And I'm going to go ahead and write this in. 124. Okay, the next one's what? 131? Agreed? The next one's a much easier one. If you need a calculator for that, you're disappointing me. And the next one at 120? So what is your grand total? Well, we have 300 and we have 44, 75, 86. Is it 386? Just doing that in my head. And then what else do you need to do? The column totals, right? Okay, what about that first column? We have a 66 and a 68, so that's 134, 135, 225? Do we agree? Well, if I can get the pen to flow. Coming off there just for a moment, Jennifer. Didn't have the right angle for this. And so if you subtract the 225 as we come back to the book from the 386, what are you going to have for the second column? Come on, you can do that in your head. 161? Now, what do you need to do to finish this problem out? What would you have to do? Somebody tell me. Let's come back to the problem so you can see it. What's the next step? Clara. Can't get summations yet. I'm missing something. I have observed values. Do you have any expected values in this? Not yet, right? So I need some expected values. How am I going to get the expected value? And let's just take the first cell. How do I get the expected values for the number of females in accounting? I know it's 68 in reality, but what should I expect? And the assumption is that the choice of major is independent of being male or female.
So it should be 62.
Okay, Sean's saying common sense says 62. How do you find it if you don't want to resort to common sense? My little formula that's on the front board. RT times CT over GT, do it. Let's come back to the data. You have 124 is RT, 225 is CT, 386 is GT. What do you get? I'm waiting. 72.28. Anybody agree? One head bob? Two head bobs? Come on, vigorously head bob. Alicia, don't go to sleep, just head bob. So you are supposed to first do the calculator. Okay, do I have any more than two people agreeing that it's 72.8? Yes. Okay, let's come off there for a moment. So I'm at 72.8. 72 what? 72.28? Okay. Now, what was wrong with the estimate of 62? Because it looks like, as we come back, half of 124 would be 62 if there was no preference because of gender. What was your problem with the analysis? You didn't have the same number of females and males in school. It was an unbalanced group. And that's why the 62 didn't work. Now, once you have that 72, can you get the number of males for expected value? Coming back to the data. How do you find that? Easily. Take the 124, subtract the 72.28, and that will give you the expected value, correct? Boy, I'm not getting very much agreement out of you. You're a reluctant group this morning. And, you know, I'd expect this after Thanksgiving because of tryptophan, but not prior to. This is a little bit unexpected. Thinking of expected and unexpected. It looks like we're going to have to get a little more aggressive with this. And leave that on the screen for a moment for me, if you would, Jennifer. I was hoping we could just do it in the text and slam our way through it. And you are a reluctant participatory group today. Or maybe I'm just being more sensitive to your non-participation. Oh, that's it. Studying for your test. I think you're dreaming of pumpkin pie and turkey and dressing and all the neat things that go with it. Accounting, administration, econ, and finance. This is the time to be an authority in one of these areas because you would have a job. This is called the Economic Recovery Team that's being created right now. And one of the professors, I think it was from Stanford University, or was it Berkeley, that just got selected from our area for that group. Okay, and we have female and male. And we had 68 here, and we expect 72.28. Let me run some numbers quickly, and then we'll go to the board. 1, 2, 4, 1, 3, 1, 11. 1, 2, 0, 3, 8, 6. Down here we had in the column total 225, and we have 161. Okay, and then I have some other numbers I need to write here. 91, 5, 61. Is that correct? And then a 56, and 40, and 6, and 59. Now, I need to have you help me out with the expected values here. We said we had 72.28, so 51, 72. Okay, so we have that. And now, you need to play the game. Again, that game is the EIs. RT times CT over GT. Will each of you pick one of these? And not all of you, this one. Okay, what do you have here, Claire? 7636? And since you got that, you can quickly give me this. What is it? 5462. That gave somebody else time. What? 64. That's right, because I have to add up to the 0 position there. Okay, somebody else for the next row. 6.41. Thank you. And 459. We got people participating. I'm pleased. You all would sit around and not help with the Thanksgiving dinner and expect to eat. Okay, what do we have for the next one? Last one. 69 point what? Daniel's going to get a second helping. And what's the next? 5805. Very good. 50.05. Do we now agree on these? Okay, the hard work's done. We need to fill in for the chi-squared value, and we need to do a couple other things, but I'll put OI minus EI, and you can do it backwards if you want. I just happen to do it this way. So we have to take the difference of each of these entries in the cell, square it, and divide by the one we just calculated. Before we do that, what is our null hypothesis here? Choice of major is independent of what? Independent of gender. And I love writing the alternates in this. The null is false. That is, you have dependency. But it's just nice to say the null is false. No, that's a conclusion. This is just the alternate. So you don't want to reject or fail to reject until you do the hypothesis test. Okay, so what else do I need here? Degrees of freedom, correct? How much do I have for my degrees of freedom? R minus 1 times C minus 1? Degree of freedom, R minus 1 times C minus 1. You had 2 columns, 4 rows, so how about a 3? So I have something like this for my density curve for the chi-squared. I want 5% here. So will you please give me the critical value, and we'll make a decision rule here so we know what we're going to do at the end. You are going to have to look in your book for the critical value. It's not going to pop out of the speaker system and say the critical value is. Anybody? Daniel's looking up. Good. A few others are. 7.81. Do we agree? 1, yes. If you aren't looking up, you don't know whether to agree or disagree. Okay, a few more head bobs. Okay. So what's my decision rule? Somebody. Reject what? H sub 0, right? If what? Finish it off, Sean. If chi-squared is greater than or equal to 7.81. So all we have to do is what? How many calculations do we have to do? 2 times 4 is 8. 8 calculations. Okay. We're going to parse this out. So front group, maybe do the first 2. This group, the next 2. This group, the next 2. And if you're by the door, you get the last 2. That's my new group of 1. There's certain non-perks being by the door. Okay, while you're doing that, and what I want Jennifer to do is just show that table again. This is the pre-Thanksgiving table. Okay, and while that's up there, bring it in a little bit tighter, a little bit more, a little bit more, a little bit. There we go. I can now read it. 68 minus 72.28. Square the difference over 72.28. And I think I'll just go down the first column. So I have 95 minus 76.36. I'll square that over 76.36. And we go down to, oh, I love the smaller numbers, minus 5 minus 641. Square it over 641. Okay, Clara's group lucked out here. Then we have a 61 minus a 69.95. Square that over a 69.95. And then I need a next column, which is going to be a 56 minus a 51.72. Square that divided by 51.72. And I'm starting to feel rushed, and I don't know why. 54.64. I think my arm's getting tired. Why did I do that? Leave the space there. I have no idea. I'm not responsible for what I'm writing, I fear. And then I have a 6 minus a 4.59, and I'm going to square that and have it over a 4.59. And finally, 59 minus 50.05. Square the difference and put it over 50.05. And throw in some equal signs. And Jennifer, you can pan over now. You just went to a different... No, you didn't? You went that fast?
I was panning while you wrote on the top line.
Huh. I wasn't paying attention. Okay. Some numbers, please. The first group. 0.253. That's all I'm getting out of that? All that work for a 0.253, and I need to get up to 7? This is not a big contribution. You can do better. Somebody that's still in that first group, so I'll go over here. Sean, you gave me the first, and somebody else at that table besides Sean? Okay. What? I don't know. We'll have to find out if anybody agrees. I'm bunch of slope. Going to the next group. The heck with them. The next group. Anybody have? Nick.
Four was it? 4.55, thank you. And, Nick? 3.92. Next group. Zero point 0.31?
No,
0.310. Oh. Okay, the other side of the table. 440. The only thing that looks like we're getting major contributions is where? The administration, where I said it didn't look like what I would expect. A bunch of optimists. Okay, you disagree in this?
no, I got 0.433. I did
Instead of a 0?
instead of a 4 0.
33, so a 0.433. Do you want to recant, Ashley? No, trust yourself, but either redo it and we'll put a question mark there. Okay, at the door, Bianca. 1.145, not a big contribution, but better than some of the others. 1, 6, and zeros. Okay, Ashley. Do you hold with the 4.4?
No, because I got something else.
Which is?
I got 0.433.
Okay, so we're in agreement there.
Yeah.
Okay, this first group of slackers. What do we have for this one?
1.354.
So you do agree with the 354. Okay. Now, what made the big difference here? The number of women going into administration. Okay? So with that said, I need to know what the total of all this is. So you just add up these 8 values, and then I can slide over, not me, but holy cow, Jennifer and I will slide over, and you have about 30 seconds to come to a number before we go to the slide music. We want to bring closure. Somebody quick. 12 point what? 5? 7. Do we reject? Yes. Thank you. And so with that, success. Jennifer, we were listening to Fleetwood Mac. What are we going to do?
Homeward bound.
Homeward bound to Thanksgiving and watch the tryptophan. Have a great